This section explains the first flavor of artificial life, why life is a process rather than a substance. Physics found mass by subdivision, cut matter into atom, then nucleus, then quark, and each part is still massive. Life defeats that move. Cut a cell, and the pieces stop living. So life belongs to no single thing. It belongs to an ensemble, and the parts carry it only together. Every substrate-bound definition, the metabolic one, the biochemical one, the genetic one, then fails, because each names the wrong invariant. Here is Atomy's turn. Life is what an ensemble does. It shares information in some physical medium and holds its entropy far below the maximum over timescales that dwarf that medium's own decay. Strip the chemistry, keep the principle, and the word artificial stops meaning fake. This is what the chapter licenses for the whole book. If life is process, then silicon is as legitimate a substrate as carbon. This section explains the founding inversion that opens Atomy's book. Biology only ever took life apart. It had one specimen, Earth's own, and it studied that specimen by deconstruction. Adami opens the entire book on the reversal of this. To know what life is, you build it. His method is synthesis, where biology's method was analysis. The living state becomes a class, and the defining invariants of that class are not recovered by cataloging the single member that evolution handed us. They are recovered by reinstantiating life on other substrates, on code, on artificial chemistry, and then keeping whatever survives the transfer. The theory he seeks is deliberately falsifiable. It is a universal, framed to be proven wrong by extraterrestrial or synthetic life. This is understanding by building, so that the definition of life stops depending on the accident of its one known instance. This part explains why life resists the method physics uses to earn its theories. Physics earns its theories by descent. Subdivide a massive object and each fragment stays massive, so the class of mass anchors in an elementary bearer, atom, nucleon, quark. It is redefined by the invariant that survives the descent, which is redefined by the invariant that survives the descent, which is inertia rather than heaviness. Life refuses the first step. Cut a living thing apart, and aliveness leaves every piece. No elementary living object exists because the property belongs to the collection rather than to its parts. Analysis is barred, and with it any definition by constituent. So the theory must be universal in the other direction. It reaches for the simplest system rather than the simplest part, specified by principles a living thing must satisfy: self-replication, information storage, low entropy, and selection. It is never fixed by the matter that realizes them. Where you cannot take life apart, you build it. This section explains how to sort every branch of artificial life that the book leaves uncovered. You sort them all by a single axis. How many units are in focus? Emulation reproduces the function of a single agent. One cricket's phonotaxis, one fish is swimming. It copies what one thing does. Simulation runs many in parallel and watches for what the ensemble does that no local rule names, its emergence. The grain differs, but the move is identical. Both copy life. Both model rather than make. This section exists to fence that modeling off from the book's own project, which is construction. The reductionist creed, high behavior from low rules, is shared. Yet Adami lets reduction halt above physics, and the thing modeled need not itself be alive. A copied part suffices. This section explains how self-reproduction falls out of universal computation. Self-reproduction is a corollary of universal computation. Turing's move was to see that a machine's rules can be written on the tape. Another machine reads, so a single, universal machine emulates every other one. Von Neumann pushes this one category up. A constructor fed a description builds the machine that description names. Feed it its own description, and it copies itself. The catch that makes this go through is that the description must be used twice, along two incompatible channels. Once it is read as instructions to build the body. Once it is copied blind, uninterpreted, to hand the offspring its tape. That double use of one string is the genotype and phenotype split, deduced as pure logic years before Watson and Crick watched DNA do exactly this. Ched, DNA do exactly this. This section explains what a cellular automaton is at its root. A local rule iterated is the whole thing. Each cell's next state reads only its neighbors, and the same rule fires everywhere at once. Yet run it forward, and global structure appears that no equation can shortcut. You must execute to know. Consider the historical arc that Adamy traces. Von Neumann built cellular automata to force self-reproduction into a formal medium. Langton then reframed the problem. Supply the necessary ingredients for life, not the sufficient ones. That reframing made the field tractable. Wolfram's 4 classes sort every rule by its long-run fate, fixed point, cycle, chaos, and the rare class 4 perched at the edge of chaos, where patterns grow rich enough to compute anything. Complexity is what iteration extracts from locality. Nothing designs it in. Ration extracts from locality. This part explains why artificial light exists at all, the wager the book rests on. Biology resists the one method physics lives by. Take the system apart and study a piece in isolation. A deconstructed organism is a corpse. Life vanishes into its constituents, and there is only one instance to study, so no comparison can separate the universal from the terrestrial accident. Chapter 1's whole survey of the flavors of artificial life, robots, swarm builders, artificial chemistries, cellular automata perched at the edge of chaos, is really a search for the one instance you can dismantle without killing it, the digital organism, rerunnable and wholly observable. The overview names the wager. The book rests on. Manufacture a second instance of life, and reductionism, with statistical physics behind it, becomes possible again. This section explains why evolvability is a property of the world you build, not of the thing that copies itself. Life needs a chemistry that is kind to noise. The chapter's move is to choose the substrate before you choose the organism, because evolvability belongs to the medium, and the replicator only inherits it. Langton's self-reproducing loop makes the problem visible. It copies itself, yet nearly every mutation kills it, because in that world, the automaton and the information it carries share one medium. You cannot perturb the message without breaking the reader. The escape is to stop hunting through cellular automata rules for a forgiving chemistry, and instead borrow one that is already computation. Universal, the von Neumann CPU's instruction set, where the biochemistry comes for free. Self-replicating code, first glimpsed in real computer viruses, is that chemistry. Tierra's advance is template addressing. A mutated instruction no longer drags its operand down with it. This section explains where evolvability actually lives and why it sits below the organism rather than inside it. The living move happens one level below the organism. At the chemistry, the instruction set, whose response to noise decides whether a mutation kills or improves, Langton hand built a self-reproducing loop, and every mutation destroyed it. Ray's fix was to strip operands and address by template, matching, an enzyme finding its complementary shape rather than an absolute address, so a mutation perturbs a pattern without corrupting a reference. Then evolution, he never designed, erupted, parasite stealing. Host, copy loops, immune hosts, wearing unrecognizable templates of full arms, race. Evolvability lives in the substrate's geometry under perturbation, not in any single organism. Engineer the world where mutation stays viable, and selection hands you the world where mutation stays viable, and selection hands you. This section explains why self-reproduction resists cellular automata, and where the escape route leads. A self-reproducing structure needs a medium that survives mutation, and cellular automata never hand you one for free. Every encoding tried so far is brittle, so essentially every mutation of a replicator yields a non-replicator. Finding a cellular automaton, rule set that is kind to noise, means searching an astronomical space of possible chemistries, together with the automata roaming them. That search is hopeless with current technology. The generative move is to change substrate rather than to search harder. You abandon cellular automata for a medium where the property you are hunting, computation, universality, is already guaranteed rather than sought. That medium is the von Neumann computer itself. Its self-replicating code first glimpsed in viruses and in Core War. You stop building the artificial biochemistry once you pick a substrate that gives it to you. This section explains why computer viruses are the existence proof that code evolves, and how Rasmussen's core world turns that accident into a controlled instrument. Computer viruses are the existence proof. Code replicating in memory already evolves in the wild, producing real phylogenies and a virus versus antivirus arms race. That arms race is analyzable by the same kinship methods used for genomes. Rasmussen's core world turns that accident into an instrument. It is a circular memory seeded with Core War's red code, a Turing-complete artificial chemistry. Its copy operation is made noisy on purpose, so the medium itself can adapt. Here is the move that generates the whole field. You do not design the organism. You choose the chemistry, and then you hunt the fixed point. Handwritten self-replicators die under noise. What persists instead are emergent networks of programs copying each other. Life becomes an attractor of a self-modifying computational medium, not a thing you place there. Origins get reframed as dynamics. This section explains why Tierra could evolve where Core World could not, and the single change in addressing that made the difference. Core World's replicators shattered under mutation because each instruction carried its own operand. A target address bolted on, so one bit flick corrupted both the operation and the location at once. Ray's move is to sever them. Addressing becomes complementary. Matching. Instructions carry no operands. A jump searches for the mirror image template, strings called NOP0 and NOP1, the same shape recognition biology, uses when an enzyme finds its substrate and it binds wherever the shape fits. Now, a mutation touches one thing, not two, and the reference survives displacement. The primitive is this. Evolvability lives in the addressing scheme, the way references find their targets, rather than in the instruction set. Decouple operation from location, let location be found by shape. Complementarity and brittle code becomes an open-ended evolving medium. This is why Tierra, and not Core World, opened the second revulsion. This section reduces the origin of life to a single, measurable quantity. Strip the mysticism from origin of life, and one number survives, the density of self-replicators in the space of possible programs. Push that density high enough, and replication stops being designed. It is found by noise. Pargellus's amoeba dials it up by choosing a benign 16 instruction chemistry where 5 suffice to self-replicate. Replicators then condense out of random code unbidden. The tell is inverted from engineering intuition. Longer programs replicate more readily, so the route runs long and clumsy, first, optimized, and short after. Afida is named here only as the workhorse the rest of the book will run on, deferred to chapter 9. Amoeba carries the argument. The whole question reduces to 2 parts, how dense and fixed by which chemistry. The generative move is this. Emergence is something you engineer into the chemistry rather than something you wait for. This section names what the coming theory will analyze before it analyses it. A field closes a 50-year loop by trading universality for tractability. Von Neumann wanted a self-replicator that could build anything, construction universal. What survives is narrower, virtual CPUs that only compute universally. Their replicators isomorphic to minimal von Neumann automata. The chapter's wager in chapter 2 is that this stripped-down thing is a minimal living system, the model organism of life theory, the way the logistic map is the model organism of deterministic chaos. That is the generative move, to make a phenomenon analyzable, keep the smallest instance that still self-replicates and discard every other generality. The overview's job in the arc is to license the coming theory by naming what it will analyze. The move forces the phenomenon into being. This section introduces information theory as the single relation that everything downstream is built from. Start from the counterintuitive claim. A symbol string carries no information by itself. Information is the entropy. 2 ensembles share their correlation, nothing intrinsic to either. Entropy, written as h of x, is your uncertainty about x, the average number of yes or no questions needed to pin down its state. Conditioning on a second variable can only lower that uncertainty. Exactly how much it lowers is the information itself, the mutual information itself. The mutual information between x and y equals the entropy of x minus the entropy of x, minus the entropy of x given y. It is symmetric, and it's always about something. This is Adamy's move for the book. A genome means only its correlation to the environment, and life is the noisy channel that stores that correlation against thermodynamic decay. Everything downstream is this one relation, read at different scales, coding efficiency, channel capacity, the eventual evolution of complexity. All of it is mutual entropy between system and world. Mutual entropy between a system and its world, read at different scales. This part explains why heredity can be treated as a communication channel. Heredity is a channel. A genome is a message. Reproduction is its transmission. Mutation is the noise that corrupts it. And Shannon's machinery, built for telegraph wires, measures exactly what a lineage keeps. The mutual entropy between parent and offspring is the information that survives one generation. This is the primitive the whole book runs on. Adami recasts the genetic channel as a binary symmetric channel with error rate p and fidelity f, so a population at fidelity f equals 1 has 0 entropy and can share none with its successor. A perfectly uniform lineage transmits nothing. Once inheritance becomes noisy, communication, complexity turns measurable. What a genome knows is whatever crosses the channel intact. This section explains how to compute probabilities for a binary symmetric channel with error rate p. A binary symmetric channel is one primitive repeated. Each bit crosses independently, flipping with probability p, surviving with 1 minus p. Every bit is a Bernoulli trial at its position, with no memory linking them. So every probability the exercise asks for factors into a product over bits. Take a particular received string. It differs from the sent, one at some fixed set of positions. Multiply p for each flip and 1 minus p for each survivor. That product is the probability of that exact string. Now suppose you want k errors anywhere in n bits. Count the arrangements, n, choose k, and multiply by p to the k times 1 minus p to the power n minus k. The binomial is just independence plus bookkeeping. The whole problem collapses to one move. Name which bits flipped. Memorylessness lets the joint probabilities separate into that clean product. The count of flipped positions is the Hamming distance between what was sent and what was received. This section explains the single move that statistical mechanics makes, the move the whole chapter exists to hand you. A population is a density over the space of its members' configurations. The individual members are not what you track. Consider the alternative. To follow the population directly, you would integrate n-coupled trajectories, which is hopeless. That computation runs longer than the age of the weighting, and you could never even initialize it. So instead you carry a single distribution function on phase space and average the quantities you care about against it. The forces between the constituents are all you supply about against it. Adami's wager is that this substitution ports intact from atoms to self-replicating code. Genotype space becomes the phase space of living systems. He claims, on the strength of that statistical physics must be the basis of any theory of complexity. The chapter gives you exactly this one move, ensemble in place of history, before any population of strings gets analyzed. There is a price, and it is worth naming. The ensemble hands you an average. It can never predict when a transition fires, nor which genotype emerges. This part explains why Chapter 4 stops tracking individuals and starts tracking the distribution. Stop following the members one by one. Track the distribution instead. A population of self-replicating code has too many members and too many interactions between them to follow individually, so you describe the aggregate knowing only the forces between its microscopic constituents, and you let ensemble averages carry the behavior. That is the entire import of thermodynamics, and Chapter 4 borrows it wholesale. Genetic populations acquire a literal temperature, an entropy, phase boundaries in sequence space, a second law, the same statistics reused, not a metaphor. Adami states the stake flatly. Statistical physics must be the basis of any theory of complexity. Everything downstream, the quasi-species, the avalanches, the criticality, is just this one ensemble move applied again. And what the ensemble move gives up is exactly the individual detail. It does not tell you which member survives, nor which genotype emerges. This section explains why mutation rate behaves like a temperature, and what the entropy that remains at zero mutation counts. Mutation rate is a temperature. That single identification is the whole move. Quench the rate to zero and the population relaxes into its ground state, and the entropy left behind is not thermal residue. It is the entropy at zero equals k times the logarithm of m of E naught, a direct count of the ground. Nernst's theorem, a statement about crystals at absolute zero, becomes a measurement protocol. In Avida, drop the mutation rate mid-run, watch the entropy settle, and read m of 0 off the limit. A non-degenerate ground state gives an entropy at 0 of 0, one fittest genotype. Leftover entropy means several equally fit sequences that selection cannot break between. This section explains where the complexity of a simple living system actually lives. A living sequence carries no complexity of its own. It borrows all of it from the world that reads it. This is Adamy's move. The physical complexity of a genome is the mutual entropy between the string and its environment, the bits that mean something to the Turing tape interpreting them, which is length minus the part that stays random relative to that tape. So complexity is relational. An object is what it does, reading of information. A string is exactly as complex as its interpreter finds it, non-arbitrary. Operationally, you never see the whole. You put a lower bound on it by counting the sites. An equilibrated population refuses to vary. Randomize the environment, and the same string's complexity collapses to 0. That is the tell that meaning lives in the coupling between string and interpreter, in the reading relation rather than the symbol. This section explains what complexity actually measures in a genome. Complexity is not in the string itself. It is the entropy the string shares with the world that reads it, the mutual information between genome and environment. A random sequence carries maximal entropy and 0 complexity. The two are opposites, and that is the whole surprise. So, complexity is relational. It is undefinable without naming the environment. The same transfer RNA means nothing outside the cell that interprets it. You measure it by counting the positions. An equilibrated population refuses to vary. Those conserved bits are the organism's stored measurement of its world. In Bacillus subtilis, transfer RNA that comes to 21 to 42 bits, everything volatile being noise. The move is Yaneda flavored. A genome is what it knows about its environment, and knowing shows up as surviving invariance. And you can watch it climb in Avida. This section explains how complexity is redefined in artificial life, and how section 5.6 lets you watch that definition move. Complexity stops being a property of the string. It becomes the amount the string knows about its world, the mutual entropy between genome and environment. Section 5.6 is where that definition earns its keep. Inside Avida, you watch the quantity move. Count the fixed sites, the bits pinned by selection, against the volatile ones, the bits random with respect to the environment. The fixed fraction is the information acquired. Every fitness jump is a matching rise in physical complexity, evolution as a pump filling the genome with environmental structure. The clean falsifier runs two ways. A flat landscape has nothing to teach, so length erodes while complexity holds. Bolt on random code and length grows, but complexity does not. This section gives the overview, the single claim the whole chapter rests on. Complexity is a two-place relation, the entropy, a sequence shares with the environment that reads it. It is not something the sequence owns by itself. Strip that relation away and the question, how complex is this string, becomes unanswerable, because the answer lives half in the tape. Not unanswerable, because the answer lives half in the tape, not in the string. Adamy's move is to subtract rather than measure. Take the string's length and remove every bit the interpreting machine could have generated for free, its randomness relative to you. What survives is meaning, the mutual Kolmogorov complexity of sequence and world. This is the same primitive as information itself, never intrinsic, always a correlation across a channel. A random string is maximally long and minimally complex. The tell that length was never the point. The point. This section explains how much information each symbol of the flawed generator actually carries. Start from the principle that a symbol carries information only insofar as it could have been otherwise. The generator runs on a rule. A zero must follow every zero. That force zero could not have been otherwise, so it carries no information. It is pure padding riding along in the stream. Complexity per symbol is therefore the uniform maximum, the base 10 logarithm of 10, which is 1, discounted by how often the source's own rule spends a free choice on a foregone one. Weight the two regimes by their stationary frequencies. Genuine draws happen 10 times in 11, forced zeros 1 time in 11. That gives approximately 0.91 of a dit. Here is the primitive. Structure is the entropy deficit. Whatever a source makes predictable is exactly what you never needed to send. Move the rule, and the correlation, the deficit, and the complexity all vanish together. This section explains how a system tunes itself to a critical edge with no outside dial. Drop grains on a pile, one at a time, always waiting for the last avalanche to finish, and the slope tunes itself to the edge where a single grain triggers a collapse of any size. Scale free. A power law. That self-tuning is the whole move. Ordinary critical points, water freezing or an icing magnet, need a temperature dial set by hand. A slowly driven dissipative system with local coupling finds the critical fixed point unaided. Here is Adami's wager for the book. Evolution is the same machine, a population poised where every genotype's growth factor vanishes. The mutations are the grains. The punctuated bursts are the avalanches, forever creeping back to the state any lucky invention can shatter. This section explains self-organized criticality, the way a simple system drives itself to a knife edge without anyone tuning it there. Take a system built of local thresholds, feed it slowly, and let it bleed off at the edges. It walks itself to the single state where one added grain can trigger a response of any size at all, and no dial was turned by hand. That state is a fixed point the pile always returns to, and yet it is the most unstable state the pile could occupy. Robustness and catastrophe. Proneness turn out to be one property, the very same property seen from two sides. The avalanche sizes obey a power law. They are scale-free, and that scale, freeness, is the signature of a system that has erased every internal length except its own boundary. Here is the chapter's wager, made for a book on artificial life. Living populations are the same machine. Their self-organizing agent is information. And mass extinctions, just like avalanches, are simply what a critical world does when it is nudged. This section explains how a sand pile organizes itself to a critical slope on its own. Drop sand grain by grain, and the pile climbs to one slope, the angle of repose, then stays there, no matter where it started. That fixed slope is the attractor, and it sits exactly at the edge of collapse. Every further grain can trigger an avalanche of any size with no characteristic scale, their frequencies falling off as a clean power law. Adami's move in this chapter is to take self-organized criticality, the sand pile of Bach, Tong, and Wiesenfeld, as the lens for evolving self-replicating systems. He reaches for it because it manufactures a critical point without anyone tuning a parameter to it. The system drives itself to the knife edge and holds there. E system drives itself to the knife edge and holds there. This section explains how self-organized criticality reduces to a single condition using the forest fire as its solvable instance. Strip the sand pile down to something you can solve on paper, and one condition survives as the whole of self-organized criticality: separation of time scales. The forest fire is that solvable instance. In Model I, trees burn, ignite their neighbors, and regrow, and it never reaches criticality. Left undriven, it settles into traveling waves whose crest spacing fixes a scale, closer to an epidemic than to an avalanche. Now add lightning at rate F, held far below the growth rate P. This is Model 2 from Drossel and Schwabel. The forest tunes itself to a steady state whose fire clusters have no intrinsic size. Their average size diverges, and this yields a scale-free power law, but only in the limit where the ratio of F to P goes to 0. Criticality asks for no fine-tuned temperature. It is simply where a system falls when it is driven infinitely slowly, on rather than by tuning a parameter by hand to some special value like a temperature. This section explains one substitution. Take the sand pile, the grains, the critical slope, the avalanches of every size, and ask what plays each role in a population of self-replicating strings. Every answer turns out to be information. The pile is accumulated, genotype content. An equilibrated population, all sharing that content, is the flat slope poised at threshold. The falling grain is a rare mutation carrying potent new information. The avalanche is the wave of invention or extinction it detonates, drawn from a distribution with no characteristic size. Criticality stops being about sand and becomes about a population held so uniform that one good idea can reorganize any fraction of it. You read off the living case by replacing energy with information everywhere in the abstract model. This section explains the two theories of self-organized criticality in 6.4 and why criticality in these systems is forced rather than discovered. Criticality here is forced rather than found by a limit hidden in the protocol. Bach's sandpile self-tunes to the critical slope only because grains are dropped infinitely slowly relative to how fast avalanches relax, the drive rate over the relaxation rate sent to 0. The two theories of 6.4 are the same statement read from two sides. Carlson's singular diffusion, where that vanishing rate makes the diffusion coefficient diverge, and Sornet's critical slope undertaught picture. The self in self-organized names, an imposed separation of time scales, a separation put in by hand, not a spontaneous one. So, the ubiquity of power laws in nature is displaced onto a deeper question. What makes a natural system separate its scales at all? The problem moves rather than closes. And you do not interrogate a living population the way you interrogate a pile of sand. Why? You interrogate a pile of sand. This section explains why evolution and a sand pile are the same system. The claim is not that one resembles the other, but that they share a skeleton. Both are systems with dissipative transport and many degenerate, metastable fixed points, driven so slowly that the system parks itself at a point it cannot hold, then discharges the accumulated strain in avalanches. The signature move is that no external hand tunes the critical parameter. The dynamics find it themselves. This is self-organized criticality. Here is how the mapping lands. Mutation is the slow drive. Genotype growth rate is the threshold. The critical state is a population of mere zero growth degenerates. One lucky positive growth mutant triggers a cascade that reaches every genotype. The fingerprint is scale-free. The times between transitions are distributed as a power law. Punctuated equilibrium becomes the generic signature of self-tuned criticality. Read the exponent of the interval distribution, recognize the mechanism, and predict the next instance.